Then if there is not, we start with demand response, which is an emerging topic in smart grid. Let's start with some terminology. Demand response is often used as a synonym for demand side management. There is a subtle difference that is not always checked by everyone, so we will also probably not follow this subtle difference, but it's important to know it. Demand response is a form of demand side management that is based on price, and demand side management is the management of consumption, of the loads. In a grid, we have seen in all the different labs we've done how to control generators. In the OPF lab, that's exactly what we did. But we can also control not just the generators, but also the load. So any control we perform on the side of the load is demand side management. And demand response is a relatively young invention where the idea was to financially incentivize users to modify their consumption by, for example, receiving some monetary compensation or a smaller tariff if they follow some signals from the utility. This is new in this form, but this has been around since the beginning of grids. So with different names, load management, and we will see that there are a number of techniques and technologies that have been used already. But before we dive into the technical details of how this is implemented, let me ask you this question. Why do you think that demand response or demand side management was invented? I propose here some potential reason. And I close the poll in a few seconds. The majority says C, and that's a good guess. Demand response was really invented to solve a problem of electrical grid that we will discuss more in a few more minutes. The main problem that is on the table here is power balance. So electrical systems must balance energy, or more precisely, power, means instantaneous production and consumption of energy instantly. In traditional grids, this is done by adjusting supply to demand. As we mentioned already, that's what we did in the previous lab. In OPF lab, we adjusted some of the generators to follow the demand here. This is still the state of affairs today. This is what is happening in most grids. However, the current technologies, the current way of doing is hitting some limits due to the penetration of renewable energies have the drawback for some of them, for wind, for solar energy, to be extremely stochastic, random. You don't control when the wind blows, and you don't control whether a cloud is reducing the production of your solar panels. So there is variability, there is stochasticity that has to be accounted for, and it causes for more needs for regulation. We'll talk more about how regulation is done and what's the relation to demand response in a few more minutes. I ask this question because very often there is a confusion in the technical literature or even in the economical literature about what is the goal of demand response. We will see some examples where also even the providers of demand response services are capitalizing on this confusion. The confusion is between energy efficiency and cost saving. The goal of demand response is not to reduce the energy consumption. It is to make sure that the energy consumption takes place at instance where it is better for the grid and for the energy producers. That's the first thing to remember. Here's a very classical motivation for demand response. It comes from a large energy provider called EDF, major energy provider in France. So it's addressing the fact that the consumption of energy is of course not constant over the days. Here is a typical week showing different weeks in the night, in winter or in summer. And we see that there is of course a strong daily pattern. We consume more in the morning and in the evening. And this is due to why we use energy for. We use it, for example, for heating a lot, for cooking and for office, also for transportation. And one of the problems is that the peak here is much larger than the average. The average is probably around here 55,000 gigawatt hour, 55 terawatt hour, and the peak is close to 78,000. So we see a significant difference between the two. When you dimension an energy system, or when you take care of managing the security of energy provision in a country, you have to make sure that the peak will be satisfied here. Otherwise, there would be a blackout in probably the worst period, which would be the winter. And that's one other problem here. As I mentioned, this problem is becoming worse because of wind and solar energy. Now, this peak is typically, in this chart, is typically due to varying consumption. When it is cold and dark, we heat more and we use more lighting. In other countries, and perhaps also in our country with global warming, in the summer, we might also use more energy for air conditioning. But there is another problem, which is due to solar energy, for example, will typically produce a lot of solar energy during the day. So in a hot summer day, there will be very low consumption during the middle of the day because the net consumption includes negative consumption equal to solar production. But if nothing is done, there will be a very steep increase in consumption at the end of the afternoon when the sun sets and the solar production stops and it is still hot and humid and people use air conditioning a lot. Then there is also a high peak in demand with a very high ramping, also very high acceleration of the demand. So those are the two main concerns from the energy provision viewpoint. Less known, but equally important, is a problem about the power distribution. The first problem is if there's not enough energy during the peak, then we have a problem. And if we could move that peak somewhere, it's called peak shaving, then we could solve the problem. But another problem is about the grid. Many grids today, most of the time, don't have congestion problem, but we anticipate that in the future, when there is more distributed solar generation and also more consumption through, for example, electric vehicles, a large fraction of the distribution grids will suffer from congestion. In the lab, in the OPF lab, we had exactly this problem due in this grid, which is a model of southern Italy, where in a rural area, a lot of solar panels were installed and causing voltage problems. Voltage problems were due in that case to overproduction. Not overproduction globally at the size of the country, but at the size of the capacity of this grid. Another problem might occur due to excessive consumption. If everyone has an electric car and charges the electric car at 7 o'clock together, then there might, 7 in the evening, then the grid might suffer from congestion. Some studies indicate that in many European countries, about 1/3 of the distribution grids would have such problems. So we also need to do something to manage the flows and the consumption if we can avoid this. The alternative, of course, is to improve the grid itself, but this may be extremely costly. If you can be afforded by changing an old transformer, that will take rid of the problem, but in many cases that will not be sufficient, or the transformer is relatively new and you don't want to pay the expense of changing it, in which case you will be confronted with congestion. So grid problems or energy provision problems are the future of grids. This is why we want to do smart grids. So the idea of demand response is to control the consumer side of the problem. So what can be controlled? Well, what is there on the consumer side? There are things you don't want to control, or you cannot easily control. The lighting, the electronic appliances, TVs, computers, the hair drying at the hairdressers, for example. You probably don't want to stop the business in order to avoid a grid problem or an energy provision problem. So a large fraction of the loads are non-flexible. We also say non-elastic. However, a large fraction of the loads are flexible. It is all the loads that are thermal. A boiler is heating water for later use. Air conditioner is cooling a house. Heating, which is very often done through some kind of warming up water. Those are all energy consumption systems that have a large inertia. If I stop my air conditioning during 15 minutes, that may solve a grid problem, but that will be acceptable to me. So those are loads that are flexible. Same for fridges that are also thermal loads. Electric vehicles, cars, bicycles are not so important, but cars certainly are also systems that have a large flexibility. The rate at which, the power at which you charge a battery must be large as long as your battery has very small states of energy. When the state of energy is high or high enough, let's say has reached 1/2 or 2/3, probably you can live with a flexible rate at which you charge your car. Data centers are also big consumers of energy that have some flexibility. So there's a question, is it right that elastic loads can be controlled while non-elastic loads are stochastic? The answer is yes. The elastic loads are, of course, the ones we are able to control. It is not possible to control non-elastic loads without having a service degradation. So the idea of demand response is, of course, we will apply to elastic loads. Whether stochastic or not, both are stochastic. I mean, when I switch on my kettle to make a tea is stochastic. When I connect my car is stochastic also. So everything is stochastic at the microscopic scale. So the issue is not so much stochastic or not. The issue is there some buffer? Is there some elasticity? Is such a load able to react to signals coming from the grid or not? That's the main difference between the two. What we will do now is we will study a number of papers that were published. Give a very short summary of these papers. At the end of the slideshow are the exact references. So if you're interested in more details in any of those studies, you will be able to find them easily online through the library services of EPFL or through Google Scholar. So let's start with the first study here that's been done in Norway. Here the idea was to prevent the daily peak. So the peak, which is in the morning, 9 to 11, and the evening, 6 to 8. And to reduce the peak and therefore reduce the dimensioning of the generators of the system, and also to avoid using peak generators. Typically, many grids in many countries are organized with very efficient and cost-effective and environmental friendly generators for the bulk of generation, using, in the case of Norway, hydro. In the case of other countries like France, nuclear energy. Whether nuclear is environmentally friendly is a debate. But typically the peaks are addressed by having generators that will work very few hours a year. So those are typically fuel-based generators. Diesel generators in the worst case, very often gas-based generators. So those are generators that have high CO2 emissions. So reducing them may be very interesting. So the idea here is simply to say we advertise to consumers that there are two periods in the day, the periods I mentioned, early morning and early evening, where the prices will be variable. The prices of electricity, which are shown on this graph here, will be extremely variable. So the average price is 5 cents a kilowatt hour. But during those periods, we let the market go and it can jump and not be multiplied by a factor of 5. So you're free to use electricity when you want, but the price you would pay during those 4 hours every day depends on the situation on the market and the state of the grid, and might be very expensive here. And users were made aware of the times at which this occurs and of the high tariffs that were published typically one day before. And this is only on weekdays. On weekends, none of this happens. So the prices don't vary on weekends. So the study evaluated this and showed here on a pilot, a number of fairly large number of customers were monitored for what they do. So you see in dark blue, in green, you see dashed green, you see the weekend, you see the effect of the consumption, which is the blue line on weekdays, and you see that there is a severe reduction of consumption at the users who participate in the program during those periods. In fact, if you think about it, we have seen exactly such a case last week. Last week, I presented a programming method called MPC to follow variable prices. So the motivation for variable prices is exactly what was done in this study here. And we saw how we could use that for controlling the heating. And we saw also that through an MPC, we were able to preheat the house such that when the prices become very high, the house reduces its power consumption. So this is perhaps more important to do it for heating systems than for appliances, because the consumption of heating systems in not hot countries like most of Europe is a very significant part of the consumption, about 1/3 of the total consumption of electricity in a country. In this study here, we use price as the signal that is sent to consumers. Not exactly. Here there is price, but also the time, because consumers know in advance at which time the price will be large. But what we want to discuss here is what's the relation between price and demand. So in this paper, they show this curve here that we will try to analyze and see a bit later. So they show the supply, what is called the supply curve, and the demand curve. Those are two concepts that we will discuss in a few more minutes. But right now, the principal model that is used here is that the level of the price on the market for countries that have a market, which is most of Europe and US, the price results in the matching demand and supply. And of course, if we do demand response, the demand is reduced, so the price is expected to go down here. This is exactly what is shown here. And the motivation is in fact that Norway is a very, very long country. So the grid, in countries that are one-dimensional, the grid is always a problem. You have that in Norway, you have that in Canada, you have that in Chile. If a country is one-dimensional, that means the grid is not very, very much meshed, and you typically need to transport energy from supply areas that may be far away from consumption areas. So in Norway, the country is divided into two price areas, and because the transmission capacities are not infinite, the prices may be different from one area to the next. We saw that when we discussed the OPF module. We saw that the so-called locational prices, which are computed as the marginal price of adding more one unit of load to a given place, may vary when the grid is limited. This marginal price is the price that is used by the market. So if you are in a part of the grid where it's not possible easily to carry all the power flows that are needed to satisfy the demand, then the price might be very high. And this is exactly what happens. And what is claimed by this study is that by doing demand response in the area that's affected by this price, we're able to bring the price down, which in some sense may mean that doing demand response is able to reduce the price to customers, which was sometimes advertised as one of the benefits of demand response, but it's a very complex system. It's not because we do demand response that the price goes down. It's a combination because we have variable prices that expose everybody to the marginal costs. That demand response is able to reduce the price. But the key thing that demand response is doing, it's able to reduce the problem of which price was the symptom. So this is a pilot study in Norway that in the meantime has been deployed. In Switzerland, there are also similar pilot studies done in various parts of the country, but there are also old systems that had been around for many, many years. Here is an example of, in our area, the kind of subscription you can have, which is based on time of use. The traditional system says that you can buy a subscription that has two tariffs, one for the peak hour and one for the off-peak hour. And the price difference may be significant. You see here it goes, the price varies depending on the place in the country where you are because taxes are different, but it goes from 14 cents to 23 cents. So a 50% difference, which is significant here. Traditionally, this was based on fixed periods. The night, typically, was the off-peak hour where electricity was cheaper. This is what you do in a nuclear country. Nuclear generators have the drawback that they produce the peak all the time. The only way to modulate them is to throw away some steam, reduce their consumption, but the amount of primary energy, the heat generated by the boiler in a nuclear plant is constant. Or of course you can vary it, but it's a very slow and expensive process. So you typically run at maximal efficiency. And of course, you consume less energy at night than during the day. So the incentive to in such grids is to have lower prices during the night. Now that more and more solar energy is coming into grids, you want to make this more flexible. So this is gradually being transformed into what is called interruptible supply, where we say, I provide you with a service that can be interrupted. I can switch off your the relay that connects your boiler, for example. And this has been typically done using in-band signals. So in Switzerland, the utilities that use such a system send a small, very, very low bandwidth signal, which is just one or two tones, or a small sequence of tones called ripples that are sent in the electric lights, in the electrical lines. This is received by a special receiver connected to a relay on the consumer side, and then the relay disconnects the systems that are connected to this supply. Of course, you typically have two supplies of energy with such a system, one that can be interrupted for your boiler or your heat pump, and another one that cannot be interrupted for lighting, for computer, etc., freezers, etc. So this is also a more flexible system than this one, where the interruption is given by the utility. So this is widely deployed in Switzerland, in some areas of Switzerland, and the utilities use this really as a way to control their grids. So they will interrupt your boiler or your heating systems. This was typically combined with electrical heating systems in particular alpine areas where you have lots of houses that are very little utilized. So heating, electrical heating, which is not very efficient from an energy viewpoint, but was deployed a lot because the investment is very small. Of course, if the utility can interrupt my heating system, I must have a guarantee for the maximum duration. So the service is available by contract, for example, 20 hours per day. That means I can be interrupted up to 4 hours by a period of 24 hours. This is more flexible. This is a first step into demand response and is widely deployed today. We may need to be a bit more flexible. These forms that I presented are really for relatively static and easy to forecast interruptions. Now we need to be a bit more dynamic, and for that we need to discuss how we control the power balance in grids. So most grids, most electrical grids are fed by very large machines that are synchronous generators, which are big rotating masses that are fed, for example, by the steam of a nuclear plant. So a nuclear plant is just generating heat, and this heat makes a steam machine that rotates a big generator that produces AC power. When such AC generators are synchronous, synchronous means that they live in synchrony with the electrical power on the grid. Now, the grid is used by people like us now, and of course what we consume is always varying. So there may always be small imbalances between the production and the generation and the consumption. So how does the electrical grid manage to make sure that exactly the energy that is being consumed is produced? By which mechanism does the grid know when I start my computer that the grid needs to produce more energy to feed my computer? Well, the first thing is the grid is large. So in a large grid, the variability is reduced because by the law of large number. But still, it's not completely removed. So the very first thing that happens is that when we have synchronous generators, very small imbalances are compensated by the mechanical inertia of the generator. The sheer mass of the rotating engine, of the rotating machine, compensates the small fluctuations, in the sense that if the demand becomes slightly larger because one person is starting their computer, for example, then the generator will sense that it's getting harder to produce that energy and will slow down. By slowing down, it will release some of its mechanical inertia. So this has a stabilizing effect. But of course, this goes only for a short period of time. When it slows down, you want to recover and get speed again. So this is typically not sufficient. And all synchronous generators are equipped with what is called a governor, which is the equivalent to cruise control in a car. The governor is some system that senses that there is an imbalance because the rotating mass is slowing down. Whenever it slows down, it gives more gas. And whenever it goes faster, it releases the gas. So this is what the cruise control does in a car, where in a car, if you want, if you set a constant speed, the speed of rotation of the wheels is exactly the target. So here, the speed of rotation is the speed of rotation of the rotor. That is, it should have its nominal speed, 50 Hertz, for example, in Europe. So in such AC grids, whenever there is a deviation, whenever there is a power imbalance, this will be immediately visible in frequency. So the frequency fluctuations are first symptoms of power imbalance, to the point that in the AC literature, frequency control is in fact the term that people use to mean power balance. How to generate power balance, how to make power balance in an AC grid is by making sure the frequency is equal to its nominal value. But this is only because we have synchronous generators. If we have a grid where there is no synchronous generator, for example, a microgrid, you go into the Alps and you have a chalet here. Most chalets today have a synchronous generator. They have a diesel generator that's very noisy. And in fact, you will hear that the speed of the generator varies as the demand changes in the chalet. For example, if the deep freezer goes on and off, then that will be immediately audible in the speed of generator. This is if you have synchronous generator. If you have your more eco chalet, then you might have solar panels and a battery. And in such systems, typically it is the battery that is the so-called grid forming inverter. That's the one that takes the role of the synchronous generator. That's the one that makes instantaneous power balance in the grid here. It does it by power electronics, by trying to maintain the voltage exactly constant, which as a side effect will generate exactly the amount of power that's needed. Of course, this is never perfect, but as a first approximation, this is what happens. Here, such a grid, of course, generates a frequency because the equipment we connect to it is made to work at 50 Hertz, but the frequency is synthetic. It's made by a frequency generator, by a PLL, and it does not fluctuate. It may still fluctuate because we're in the analog world where everything is imperfect, but the fluctuation does not have to do with the power imbalance. So in such a grid, there's no point monitoring the frequency to know whether there is power imbalance. If you want to manage the power in such a grid, which you will need, of course, to do, the grid forming inverter will take a great part of this, but of course, if you live on a battery, the battery will not live forever. It will drain if there is a large power imbalance. So you will need to compensate that by other mechanisms. We have seen, in fact, such mechanisms in the lab. If you remember, we had one of the mechanisms, which is affine feedback control, where we monitor the power consumption on some of the buses, and we give instructions to the battery and to other generators on what they should do to compensate for this power imbalance. So that's another type of mechanisms that is typically done in microgrids. Here you see that we do not use at all the frequency. We use a grid forming inverter, and we use direct power monitoring and what is called agent control to make sure power balance takes place here. But in large interconnected AC grids, country size, the modes of controls are based on frequency. Here is how frequency is, here is how power balance is given. So this slide, this drawing is borrowed from ENTSO-E and OFEN. This is showing what happens when there is a large power imbalance. So power imbalance occurs due to variability and randomness. Variability is the fact that we do a forecast of solar generation, of power consumption by users, and this forecast is of course never 100% correct. And when there will be a lot of electric cars, then we will have more jobs for smart grids, because then those variability and stochasticity will be larger, because it will be much more difficult to forecast the power consumption, given that now it will also be related to mobility. So you will need to forecast football matches, going on vacation, on weekend, the weather, etc. So the forecast will always help, but will never be perfect. So we need what is called a reserve here. A reserve is some amount of generators, of generation, that are just here to compensate for the fluctuations. And the reserve is traditionally split into 3 timescales. The primary reserve, or also called instantaneous reserve, is the generators themselves. So all generators, not all, nuclear generators typically have a hard time providing a lot of reserve, but all generators try to provide, as I mentioned before, through their governor, some adaptation of their output power to the state of frequency. So they're equipped with a droop control, and whenever the frequency deviates, become larger than the nominal value, they slow down a bit. When it becomes larger, they stop a bit. So this is, they accelerate, sorry. So this is the primary reserve. This is the instantaneous control, and that keeps things fine as long as, one, the forecast is correct, and second, there is no unanticipated event. What are unanticipated events? It may be a major forecast error, This happens once in a while, in particular with wind energy. It's very hard to forecast. It's harder to forecast when exactly a storm or a very strong period of wind will come and what the intensity will be. So there may be once in a while weather forecasting error. But the most frequent source of such large fluctuations is breakdowns. If there is a fault, and this is what this picture is showing, here it's assuming a power plant outage. Many countries have an AC grid which is based on a small number of very large plants, nuclear plants or also coal plants. Now, each of those plants may have an outage. In nuclear plants, if there is the smallest security concern, then we might stop the production. But other plants are not also immune to problems. So assume here there is a major plant outage, you lose 1 gigawatt of power in France here. So that happens at this time here. You will see there is an immediate drop in frequency that cannot be compensated by primary reserves. So all generators will try to produce more, but since there's a loss of 1 gigawatt, there's not enough in the fluctuations band of the primary response. It's not possible to recover this. So this will not be sufficient. For that role, there's another type of reserve, which is called secondary reserve. So it's the hot standby reserve, where this is based on the surveillance by what is called transmission system operators. In every country, there is one or several transmission system operators. Those are entities that are responsible for the security of the entire grid. In Switzerland, there is one called Swiss Grid. So Swiss Grid monitors the frequency primarily and gets also information from what happens in all the major generators of the country, all the nuclear plants, for example, but also what happens in all the neighboring countries. Whenever there is a problem in Switzerland, for example, in that loss of a generator, in France it's similar. There is a TSO, transmission system operator. In that case, the problem was in France, so that everyone in Europe perceived the problem, so the frequency has dropped here. So the first thing I should say is that, as we see on this picture, when the frequency drops, it drops everywhere. The frequency is not exactly the same everywhere in a grid, but almost. So if there is a frequency drop due to a power outage in France, the whole of the European interconnection will see the frequency drop here. So all generators will activate their primary reserve, but here we see the drop continues, and then it is in principle the TSO for the country where the problem occurred to activate the secondary reserve, so the hot standby. And this is done by sending a signal to generators that are in hot standby. Hot standby means those generators are able to instantly produce more or less, by the way, here. So all those generators that are in hot standby, those generators can be, for example, gas turbines that are equipped with variable generation. There can be also some hydro generators that are equipped with a variable generation. Not all hydro generators or gas turbines have variable generation. Some are optimized for producing the maximum power, but it's also possible to equip them with productions that make them flexible. So there must be in every country a number of these flexible generators. Such generators are paid for being in standby. So they're not just paid by the energy that they produce, they are paid by the power reserve that they give. So even if they don't produce anything because they were never called, they will still get some revenue here. That is called a reserve market. So the reserve receives an explicit signal for the secondary reserve, as opposed to the primary reserve, where here, that's the beauty of the AC grid, you don't need to send a signal to all the generators because they all are able to monitor the frequency. So this is what happened here in France after some time, or almost immediately after the French TSO has sent to all the reserves it has a signal to increase their power. And then the power is increased. This has an immediate effect, but it takes a few minutes to have full deployment here. If you provide a secondary reserve, you do a contract with Swissgrid in Switzerland that will say you must ramp up very quickly up to some level of power. And if you've really lost 1 gigawatt of power, then those reserves that are here to solve the problems, you want to keep them because another problem might come later. So you want still to replace the primary problem in a more permanent basis. So this is why you have a tertiary reserve, which is typically what we would call cold standby. Those are generators that are not rotating, that are not able to work instantly, but can be mobilized in a few minutes. After a maximum in Switzerland 15 minutes, they should be able to produce. And then they may be required to produce for some hours of time. So this is what will happen here, and we see that gradually the tertiary reserve has been fully operational here, and then the frequency fluctuates again around the 50 hertz value. So the effect is that we've replaced the generator that went down by a tertiary reserve that will also, of course, need to be turned down when the failure here is repaired, if the failure is repaired soon. So this is the important thing to remember when we will talk about examples of demand response. This is how what is called reserves or regulations services, or also frequency control. For the reasons I discussed a few minutes ago, those types of reserve services are called frequency control because the way we view them is as the goal of them appears to be to bring the frequency back to 50 hertz. But remember, bringing the frequency back to 50 hertz is not because frequency, like voltage, is something important for things to work, but it is because the deviation from frequency is a symptom of power imbalance here. So the idea is that we use generators for providing this type of service. But there's an old idea that has been pioneered in particular in the UK. The UK grid is not part of the figure I showed you a few minutes ago. So the UK is an island. The Great Britain, not the United Kingdom, but Great Britain is an island also from the electricity viewpoint. So it's a much smaller domain than continental Europe. The same is true for Ireland. Northern Ireland and the Republic are another island, which is even smaller and more interesting from electricity viewpoint because it is much smaller. So in those two islands, there has been a proposal that has not found its way, but it's frequently resurfacing, to use the fridges, the refrigerators, the fridges, as a way to provide primary reserve. What's the idea? Well, the first idea is that if you have a fridge at home, which probably you do, you have a device that's working 24 hours a day. It's not working uninterruptedly. A fridge compressor typically goes on and off, but it does it randomly. And if you aggregate that as a scale of a country, you have a few million fridges, even in Ireland. And these million fridges are constantly working at perhaps 20, 30 watts in average. So this is so you have a constant source of consumption in a country. And the idea is that if we want to increase the amount of primary reserve, then we could modulate the fridges. When the frequency goes down, we could ask the fridge to delay the compressor the next time when the compressor will come up here. So this has been studied in detail, and in fact some chips have been implemented and they exist. So we can equip, some fridges are pre-equipped with some of those chips. So the chip needs to monitor the frequency of the power and then do the following. Here, this is essentially saying that it monitors the frequency, this is a deviation for frequency, and how much time the frequency has been deviating. So if there is a frequency that is very large, we consider that we should immediately do something. If you have a small deviation of frequency, we wait for some time before deciding to do something. So this is what the chip on the fridge does. It sends a signal to the electronic that controls the compressor, and the signal will manipulate the on-off cycle, which is shown here, when we are in the control region, that means we should reduce the consumption of this fridge. Then the compressor will be put off after some delay that is typically random to avoid synchronization of all the fridges here. So after a small but random delay, the fridge will go off, and then it will remain off. Of course, there's a maximum period because it's a fridge, so it must keep the temperature within a certain band. That's very much the same problem as we had with the MPC problem in David's house we saw last week. So it's exactly the same problem. If the temperature goes up, then you want to have the fridge work again. So in this very simple model, it's simply done by a timer. There's a Tmax off. If you allow the compressor to be off for a small amount of time, here around 2 minutes or even 1 minute and a half. So if that happens, then the fridge must go on again. So you see that the time over which we can play is very short, but that is compatible with primary frequency control. And the study that has been performed here was to say that on the case of the UK grid, this would be equivalent to 1 gigawatt of reserve. So we can save 1 gigawatt of diesel or gas-based generators if we equip all fridges in the UK with this here. Similar studies have been done for primary reserve with heating fans, even more impressive. So this paper here by Howe, Main, etc., showed that a large fraction of the secondary reserve can be provided by air conditioning in building by simply controlling the speed of the fans. The fans appear to be one large fraction of the consumption also here. Voila, so that's our first example of demand response where we could replace at the scale of a country, which is large but not immense, like the UK, 1 gigawatt by simply managing more intelligently their consumption, which is exactly the heart of demand response.